Welcome, students. Grab your notes and get ready because today we are embarking on a really fascinating digital evolution journey. Consider this explainer your ultimate masterclass study guide. It's designed to help you completely conquer these absolutely crucial information technology and cybersecurity exam points. We're going to break down these massive, complex systems into their core components so you can truly understand exactly how our digital world operates and, more importantly, how it stays secure. So, here is the exact roadmap we're going to follow today to conquer this material. We'll go in chronological order, starting with IT history and society, then how AI works, followed by AI ethics and risks, cryptography and authentication, and finally, network security and response. Section 1, IT history and society. We began our journey by looking at how computing shrank from literally room-sized machines to global networks, and how this physical evolution entirely transformed our daily lives. Okay, here is a major exam memory point you'll want to highlight. At each one of these historical stages, IT didn't just get smaller and faster, it introduced a brand new technology that radically changed how society communicates, works, and does business. In the 1940s, we had the ENIAC for hardcore scientific computation. By the 70s, PCs actually entered our homes. The 90s commercialized the internet, making information truly global. Then the 2000s gave us smartphones, and from the 2010s onward, cloud computing turned IT into this widespread, invisible service we all use every day. Now, this incredibly rapid historical timeline is driven by Moore's law. That's the observation that the number of transistors on a chip roughly doubles about every 2 years. But here's the catch you need to know for the test. Recently, transistor miniaturization is approaching a hard physical limit. If we make circuits any smaller than they are now, we start facing quantum tunneling and power leakage issues. Basically, we literally can't keep shrinking them indefinitely. To ground this history in reality, let's just look at the social changes driven by all this tech. Think about an ordinary day today. A student in Egypt can check their messages on a social networking app, pay for their breakfast with a cashless app, join a lesson through online learning, and order a book via e-commerce. 20 years ago, almost none of this was possible. The technology literally drove the societal shift. With that context, let's rapidly define some emerging technologies that are pushing the boundaries of what's possible today. We'll start with edge computing. As we rely more and more on the cloud, annoying delays can happen. Edge computing solves this by processing data right there on the device itself instantly, instead of sending it all the way out to a central server and waiting for a response. Which brings us right to autonomous driving. So, the crucial point here, and a highly likely exam question, by the way, is the relationship between these two. Autonomous driving absolutely requires edge computing. Why? Well, because a self-driving car needs to make instant life-or-death decisions. Even a tiny 0.1 second delay sending camera data to the cloud to figure out if it should brake could lead to a fatal accident. Processing has to happen on board the vehicle. Next up, keep these two distinct for your exams. AR, or augmented reality, just overlays digital elements on your real surroundings. Think of a digital map floating over the actual street you're walking on. VR, or virtual reality, on the other hand, completely replaces reality. It immerses you in an entirely computer-generated virtual space. Basically, remember it as overlay versus immersion. We'll wrap up our emerging tech with quantum computing. Remember earlier how we said Moore's law is hitting a physical brick wall? Quantum computing is the proposed solution to break through that wall. By using qubits and the principle of superposition, which means being a combination of a 0 and a 1 at the exact same time, it enables massive parallel processing to dramatically speed up incredibly difficult computations. Section 2. How AI works. Now we're going to transition from hardware and networks right into the brains of the modern operation by looking at artificial intelligence. A massive misconception out there is that these are 4 totally separate technologies. They aren't. Notice how they are actually nested categories, kind of like Russian nesting dolls. AI is the broad, overarching term for intelligent computer behavior. Inside that is machine learning, which learns patterns from data, like your email spam filter. Inside that is deep learning, using complex neural networks modeled on the human brain for things like autonomous driving vision. And inside that is generative AI, which uses deep learning to actually generate brand new data, like ChatGPT. Section 3, AI ethics and risks.
As we can clearly see, AI is incredibly powerful at finding patterns in data, but we have to exercise extreme caution when human privacy and final, real-world decisions are involved. Let's look at those risks.
The most famous risk is called the black box problem. This happens when an AI gives you an answer, but it's entirely unclear how it reached that judgment. Think about it. If a doctor uses an image diagnosis AI, and the AI says a patient is sick, the doctor absolutely needs to know why. This is exactly why researchers are rapidly developing explainable AI, or XAI, so humans can actually look under the hood and understand the AI's internal reasoning. To safely navigate this wild new world, you need to lock these 4 AI ethics principles into your memory: fairness, transparency, privacy protection, and accountability. We desperately need these to combat something called algorithmic bias. That happens when biased training data leads to discriminatory AI decisions. For example, if a hiring AI unfairly evaluates a particular gender based on historically biased data. We need fairness and transparency to stop that in its tracks. Section 4, Cryptography and Authentication. Let's move to our next module and see how this amazing, intelligent digital world is actually locked down and secured, starting with how your private data travels safely across the web. Okay, you absolutely must know these 3 stages of HTTPS communication. First, connection. The web server sends over a digital certificate and a public key. Crucially, your browser uses a certificate authority to verify the server is actually authentic before it does anything else. Second is key exchange. Your browser creates a common key, encrypts it with that public key, and sends it back. Third is data communication. Now all your actual data is securely encrypted using that shared common key. Now, you might be wondering, why go through the hassle of using 2 different types of cryptography? It's a great design question. Public key cryptography is incredibly secure for sharing keys, but honestly, it's slow. Common key cryptography is much, much faster for exchanging large amounts of data. So by combining them, we get the best of both worlds: maximum security during that initial handshake and blazing fast communication speed while you're actually browsing the web. But listen, secure communication means absolutely nothing if someone just guesses your password. That's why multi-factor authentication is the standard today. It prevents unauthorized logins by requiring 2 or more distinct factors. And note, this doesn't mean just 2 passwords. That's just knowledge twice. It has to mix categories. So something you know, like a password, something you possess, like your phone for an SMS code, or something you are, like a fingerprint or a face scan. Section 5, Network Security and Response. Finally, we're going to look at how organizations build defensive architectures and, most crucially, how they react when an inevitable security incident occurs. What we're looking at here is the core of defense in depth, the strategy of layering multiple security measures. A firewall blocks bad traffic right at the entry. A VPN encrypts the communication path. A DMZ separates public-facing servers so if they get hacked, the internal network stays safe. An endpoint antivirus protects individual laptops. Why do we layer all this? Because the old perimeter concept of the inside of the network is safe is completely dead thanks to cloud computing and remote work. Today, we use a zero-trust model. That means literally every single access request is verified, even if it comes from inside the building. Even with all that, breaches still happen. When an incident occurs, like data tampering or a major service outage, you need to memorize this exact 6-stage order for incident response: preparation, detection, containment, eradication, recovery, and prevention. Do not mix these up on the exam. Think about it. If you rush to stage 5, recovery, before you actually finish stage 4, eradication, the malware is still sitting right there in your system. The incident will just happen all over again. You also have to realize you can't fix everything at once. That is exactly why security professionals use risk assessment. The formula is simple but vital. Risk size equals the impact of the damage multiplied by the likelihood of it happening. When you're managing security, you always prioritize your limited budget and time on risks that have both a massive impact of damage and a high likelihood of actually occurring. Now, to bring this all together into a complete picture, look at this scenario. What is really interesting about this question is that it tests literally everything we have learned in this explainer, from the digital convenience and speed of modern IT infrastructure all the way to the very real cybersecurity risks, privacy concerns, and network vulnerabilities that a fully cashless society would face. So I want you to pause, think like a systems engineer, consider both the immense societal benefits and the critical security risks, and go ace that exam. Keep learning, keep questioning, and I'll catch you in the next explainer.